Hey, students, here's another, I think, a good one. That, like I said, I didn't get a chance to do a supplemental run, but I thought maybe this would be better to maybe jump on a bunch of these homework solutions and help you out on ones that I anticipated. I did get a chance to talk about series and parallel in class, so that was good. And I actually did a calculation for series and parallel. What I didn't do, though, which always makes problems challenging for students, is, well, what if the two are happening at the same time? Or maybe those two are happening multiple times at the same time. And that's what this is. This one, you got to recognize that. For example, you look at this and it says here, find the total capacitance of these combined capacitors. And, I showed you examples with just them in series and then in parallel. And this one's asking you to think deeper about it. It's kind of like I've, showed you how to hammer, and I've shown you how to saw, and now I say, go build a doghouse. It's like, whoa, you didn't say anything about a doghouse. You just talked about hammering and sawing it. And I said, well, yeah, but that's all you need to know. If you put a bunch of hammers and a bunch of sawing together, you get a doghouse. But it takes a lot of pieces putting together. And that's what we have here. So you know about series and parallel. In fact, I'll just review. The easiest one is, we said, when capacitors were in parallel, you just added them, however many you had. And the book had 3, and I did 2. But when they were in series, you added the reciprocals together. And if you remember, I did 2 and your book did 3. Okay. And I actually, like I said, measured them and then hooked them up and then measured them to show you that the math actually worked. Okay. And we'll do a lab on that. But on this one, then, we've got all of this going on at the same time. And therefore, probably the most challenging part is saying, well, how do I recognize if something is in series or if something is in parallel? And let me start with the series. The math is harder on the series, but the idea of a series is easier, because series, as I said, is just one flowing into another. And so if you have something connecting the two, and it goes from one directly to the other without being able to branch off and go somewhere else, and we call this a node, then it's got to be in series. And so as I begin to look at this right here, this just stands out. This 5 and the 3.5 are in a series. They just, one connects right to another. Now, sadly, that is the only ones that would be in series, at least at that point, because, like, if I tried to go from this one here, it branches off with a node this way. So, bummer. However, let's talk about parallel. So, parallel, the math is a little bit easier, but recognizing parallel might not be so simple. I like to say this. If you started down, and in this case I'll say below, but it could be to the left or to the right, but below, and you went one path, a parallel path would be an alternative way. And if all you did was get one capacitor, in other words, there's not another one there along the way, then you would say those two are in parallel, because you went this way and went through, say, capacitor 1. Then you went this way and only went through capacitor 2. And so if you study this carefully, you can see it right here in the 0.75 and the 15. You could start here and say, okay, well, I could go up that way, or I could go around that way. I've got 2 different paths. And this goes through just one capacitor, and this goes through the other capacitor. So these two are in parallel with each other. Okay? So these two are in series. These two are in parallel. And really, that's all I have at the moment. But let's do a calculation. So let's find out what these two are equivalent to. And so I'm going to use this calculation. This is what I was trying to show you in the lecture. Take advantage of this reciprocal key and put in your 3.5 and then just hit reciprocal key. So that's right there, that's reciprocal. And then you can just hit plus and then put in the other one. And so I've got 5 and hit the reciprocal key. And so there we go. I just added the reciprocals together. Now, of course, this says when you add the reciprocals together, you get the reciprocal. So to get the total equivalent capacitance, take the reciprocal of that, because the reciprocal of the reciprocal is back where you started. So this is saying about 2.06. And we're in units of microfarads. So these two together are equal to 2.06 microfarads. And these two together, we don't even need a calculator for that one. You just add them. And so these two together is 15.75. And again, in units of microfarads. And like I said, it almost seems like, okay, well, what about these other ones? And maybe they're not easy to see quite yet, but watch this. I'm going to put these two, the equivalent of it. So that's the 2.06. So instead of drawing 2 capacitors, I'm going to draw just one. Now, I haven't done anything with the 8. So I'll leave that alone. And I haven't done anything with the 1.5. So I'll leave that alone. But what I did do is say these two together are equivalent to, and so I'll just draw the equivalent. So sometimes we refer to this as an equivalent circuit. This, of course, looks like 4 capacitors, and of course the original one had 6 capacitors. So I'm not saying this is the original circuit, but what I am saying is these 4 capacitors are equivalent to these 6 capacitors because I put those two together and those two together. So I've lost or reduced it, if you will, to 4 capacitors. But see, what's nice then is there might be an equivalent of this equivalent. So I call it the equivalent of the equivalent. And maybe you can see it right here. This right here, hopefully you recognize in this picture, one leads right into the other. This is the idea of series. These are in series. So let me find out what that is equivalent to. And so we've got this reciprocal sum we've got to mess with. So it's 1.5 reciprocal, add to 15.75 reciprocal, enter, and then, of course, take the reciprocal of that. And so I would say that the equivalent of these two is 1.37. And in units of microfarads. And you can draw it, but I'm kind of hoping it stands out already. But again, this is an 8. I didn't touch it. This is a 2.06. Didn't touch it. But this right here is equivalent to a 1.37. So you might call this the equivalent of the equivalent. Okay? And of course, now we're down to 3 capacitors. Now, of course, it makes sense because we first combined 2 here and 2 here, so that eliminated 2. And then 2 more combined, so now we've eliminated a total of 3, so we've got 3. And this right here, again, kind of hoping you see they're in parallel. Maybe if I look a mark up here and I go up here to the top, I could go this path, go through that capacitor, but I could go this path and go through 1 capacitor. Or I could go this path and I go through 1 capacitor. So all of these are alternative paths. They're in parallel. To get over to here, you wouldn't go, through one and then through another. You just go through one. Or you go through this one. Or you go through that one. So it doesn't really matter which one. You go through them. So all of these are in parallel. And so you would just add them all together. So this one's in my calculator already. So then I will add the 8, and then I will add the 2.06. And so this is the 11.4. And again, still using microfarads. And I guess ultimately now we've got to the bottom line that these 3 are equivalent to this one, that is 11.4 microfarads. And that's really what the circuit is saying here. Find the total capacitance of these combined capacitors. This is what it is equivalent to, if you hooked up like I was in class, a voltmeter from here to here, your voltmeter, and for that matter your circuit, doesn't know whether you have these 6 or these 4 or these 3 or this 1. Either way, it just knows that the total capacitance, the total effective capacitance of all this is 11.4 microfarads. So that one illustrates really well the idea of using, at the same time, we've got a circuit of things of series and parallel, and we can keep reducing it down until we get to what is the whole thing equivalent to. And we just go through a series of steps, combining things together. And then, of course, the hard part is recognizing it. Is it in series or is it in parallel? All right. Hope that helps.